It looks good, Arun.
Thank you very much. Good morning, good evening, everybody. Thank you for this really great workshop. Loving the talks, and we're going to just give you a flavor of what we're doing at tomorrow.io. Tomorrow.io, as Kevin said, is part of Epic, and we are teaming with the Epic team on Eagle and developments for with the Anemoid framework. What we're covering here, since that's already been covered, are the other areas where we are seeing machine learning and how tomorrow.io is working on it. It's a large team, and so I have done what any good manager does, is when I given a task is to delegate it. So this talk will be distributed by a few people. We'll be covering these things, and then some of them are listed over here. I'll let them come on and introduce themselves as they come on to the talk. Some others, being Friday, had kid duty, so I'll be covering for them, so probably not do as good a job. But anyway, I'll move on. I just want to give you a small idea about what we are as a private sector company. I was with NOAA for a long time, moved to tomorrow.io about 2 years ago, and it's been a great ride. We are essentially, we launch satellites, we're running models, and we have a platform. So we cover all three aspects of it. Building observations, launching satellites, building the observation database, looking at weather modeling in both physics and AI ML space, and then finally having a platform where we can do weather insights. We're only going to cover 1 and 2 here, and our main focus is going to be on the ML side. So there is a large area of the company that's doing data assimilation, classical data assimilation, regional weather modeling that we're not going to cover over here. So again, broadly, where does tomorrow.io sees AI being important? We see AI as being important in all aspects of the platform, end-to-end weather enterprise. So directly from our constellation, how we're using ML techniques to develop products, enhance the satellite products, using it for our nowcasting, which is what we call unified precipitation, the forecast model, and the thing that we are very, very excited about is essentially ML in data assimilation. And we'll cover a little bit of this just to give you a flavor. We're happy to talk more in detail on this. So I'm going to just start with the constellation. So tomorrow.io has been launching satellites, microwave sounders. We've seen a few LinkedIn posts on it if you have not. Essentially, our sounder is a upgrade. We call it 1.1, Tropics 1.1. It's a 6U bird. It's got 12 channels. It uses a digital spectrometer, which is what it's slightly different from the tropics. And as of right now, today, we have launched 7 of these. The first one worked for 2 months and it failed, but we learned a lot from it. The other 6 are giving us data. We typically, for us, time is money. So from launch to calibration, validation, and having this operational, we're typically down to about 30 to 45 days. It's a lot of this work is thanks to Joe and Ethan. And what this is trying to show you is on top all the government satellites. These are the NOAA and NASA satellites. And on bottom is the same animation, but now with the addition of the TMS satellite. So it improves, and you can see the arrow there is an extratropical storm. And what this animation is just basically showcasing is how much more data you get just by adding the tomorrow sounders. So, of course, once we get into the satellites and the product, so this just kind of gives you an idea about when these data were launched. So S1, which is our first one, worked for 2 months, failed, but the others have been launched on regular basis, and they're giving us data, operational data feed right now. This data is under being evaluated by the NOAA Commercial Weather Data Pilot Program. Our aim is to have about 12 or 14 of these flying when we're all said and done by the sometime middle of next year, and that will give us an hourly revisit rate. So an incredibly enhanced view of the world from space. So how do we take these observations and we connect them using AI? One of the things that we've started using is, if you look at all sky radiance assimilation framework, they're computationally expensive, requires extensive data thinning. So one of the things that we've done is started to simulate TMS observations. How we do it is we take essentially train our data with numerical model solutions. What we have used is a high-resolution global nature run from NASA to do that training, using that to build level 2 neural network retrieval products. This is basically an alternative to the Mayer's approach that we have, and there's a publication in preparation for it. What that gives us is essentially an example of a retrieval. What we're looking at here is a mid-latitude bomb cyclone and the temperatures at the different vertical levels that we get from the satellite observations directly, and products like the ice, liquid, water paths, as well as the precipitate and storm top height. All of these are again derived using neural network techniques. Of course, we're now looking to expand that and build up on with newer ML methods. A publication on this will be coming out in about a couple of weeks, hopefully in preprint. So just watch out for that. And then, of course, the question then comes is how good is this data? We've compared that with the radio sounds. It's there's a lot of words here. I'll let you read it once the presentation is available. But broadly speaking, it's in line with essentially what we get with the Mayer's algorithm. We hope to expand on this capability beyond what it currently is. So that's one example of where we're using ML methodology to improve our products. We think this has got a lot of promise, and we think that by expanding on the ML techniques, we're just kind of scratching the surface. We can really expand the use of AI, not just in forecasting, but in building satellite products. So that's something to just keep an eye out for. That's one of the areas that we're super excited about. And then I'm going to just go ahead and let Brandon speak about our unified precipitation. So Brandon, if you're there, can you take this on?
Yep. Thanks, Arun.
Right.
And thanks, everybody, for sticking around towards the end of the day for this. So, yeah, unified precipitation is our solution for blending together all the different precipitation estimates that we're getting from ground-based radar, geostationary satellites, and, of course, our microwave sounders. It's a really big driver for us as a business because a lot of our customers are interested in these rapidly updating precipitation estimates. They really can't get it from any other source, so globally. So this is a really big part of the business for us. And so what we provide are real-time precipitation estimates globally from satellites, and then we drive a nowcast from that real-time state out to 6 hours using optical flow. And we also have probabilistic forecasts built into the nowcast that will give on our platform. It gives a range of the possible precipitation values, and yeah, it really helps our customers prepare for all possible scenarios. So this is just showing, the geostationary satellite imagery that we get is it's very broad, but the resolution isn't as good as we could get from microwave sounders. So we anchor our algorithms with the geostationary satellite data, and then that microwave sounder observation gives us some really good 3D information. And then where radar networks are available, we blend that in. And that's the gold standard. And of course, so here's this. This is showing our convolutional neural network-based architecture, where we blend in the geostationary data with that passive microwave sounder data. So in areas where the passive microwave sounder data is available, we just stack that on top of the geostationary satellite data. And it runs auto-regressively, so we look back 8 time steps. So for GOES and Himawari, that'll be, they update every 10 minutes, so it'll be 80 minutes. And then for Meteosat, they update every 15, so we look back 2 hours. And then we trained on MRMS as the target for that CNN. So this is just showing like our next gen solution with the satellites. And for example, in the Intermountain West, we get much better coverage because there's radar gaps in these areas where there's beam blockages, and so the satellites fill in these gaps for us. And let's see what else. And we're beating iMerge early by up to 10% by incorporating our satellite data into these precipitation estimates. So this is a case study of Hurricane Helene from 2024, and it's showing the left side is MRMS, and then the right side is our unified precipitation product. So you can see with the satellite-based precipitation estimates, we're really getting that global coverage. So this is really great for our customers. And so here is this is the radar example of unified precipitation. So this is showing how the optical flow is working, and it has multiple ensemble members. So that's how we do our probabilistic insights. Yeah, and this runs at every 6 minutes out to 3 hours, and then we use numerical weather prediction past 3 hours. Yeah, and we can actually use transfer learning. So we trained on MRMS data, and then we can transfer that knowledge that we learned to other domains that don't have radar coverage. So that's pretty cool. And then go to the next slide. Okay, I guess yeah, I got ahead of myself there, but so yeah, we transferred this to global scales. Most of the globe doesn't have a reliable radar network. You have NextRad, Opera in Europe. Australia operates a radar network. Some radar networks in the South Pacific, but Africa definitely has a lack of radar coverage. So we're covering that radar gap with our satellites. And yeah, this is just showing the skill of the radar-based nowcast versus satellite-based, and of course the radar is definitely outperforming satellite. But when you compare our satellite-based nowcast versus iMerge, we're definitely outperforming that sort of nowcast. And this is a figure that comes from a paper that's in review right now that we submitted to the Journal of Hydrometeorology. So this shows when we had an overpass with Hurricane Helene, we got a nice scale bump that stuck around for about an hour and a half, which matches with our autoregressive window that we look back. So yeah, it's powerful because it's a near real-time algorithm. So even if our latency is say 30 minutes, we can still have an impact in a real-time precipitation estimate. And this is just another figure showing just different thresholds, how we perform on different thresholds. And sorry, this was Hurricane Milton. And let's see what else. So yeah, we do have this paper that's in review. It's on archive. So if you have a chance, go check it out. You can see how the deep learning is working and how we're synthesizing multiple data sets into a single retrieval. And yeah, this is a recent example of our next gen algorithm with Hurricane Eric as it was about to make landfall off the coast of Mexico. So you can see the gray overlay is where we had an overpass of the microwave sounder. You can kind of see in the last frame, the intensities drop off as we lose that coverage. So it's really making an impact. And you can see this right panel. This is a data denial experiment where we did a difference between when we used the TMS data versus when we didn't. And you can kind of see as it overpasses, we're revealing some of the structure within that hurricane. So yeah, it's pretty powerful data, and we're just using all the methods that we have at our disposal to take advantage of that data. So with that, I'll pass it back to Arun.
All right, thank you, Brandon. I mean, again, this is just a brief introduction of our nowcasting capability that we're using with our satellites. And I'm going to pass it on to Forrest, who's going to talk about our ML modeling capability in the regional domain. Forrest, just let me know when you want me to move the slides.
Sure, I'll provide a little bit of a linkage with the previous slides. So the unified precipitation gives us a way to leverage a lot of the geostationary radar and our own constellation in a cohesive framework to improve precipitation. We also, of course, want to be able to yield a positive impact on other core variables in the forecast system doing that. And so the big thing to highlight here is this sort of framework for getting all the way from constellation data to customer use cases. And there's, of course, many different avenues that needs to take, from running global models to running precipitation-specific products. And what I'll talk about, which is our regional model, we've termed this focus. The C stands for CORDIF to just set the kind of expectation there. You've seen a lot of presentations relevant to that. And I'll kind of try and take some lessons learned that are really similar across our approach and what we've seen presented earlier today. I think learning a lot of the same lessons as we execute through this. For us, the big thing is really to be able to take what's available and provide a positive impact for our customers, whether that's improving the stability of products, the uncertainty information, temporal resolution, adding variables. And so you'll get a bit of a flavor of those different efforts in our work. So if you can go to the next slide, Arun. So if this slide's looking fairly familiar to you, you've probably seen quite a few different HER emulators today. This is another one. What we're really motivated here is to be able to have a diffusion-based approach to really learn that physical representation as previously simulated by WRF models, right? So we know that they've got a good physical representation. They're just expensive to run, and we're motivated to be able to run large ensembles that can help us sample uncertainty space while still benefiting a lot from the physical representations therein. So when we look at something like this, a squall line coming across the central US or a front, we want to be able to capture the location of precipitation, where it could occur, as well as the physical representations, how it'll impact other fields like wind gusts that may affect our customers through down power lines, or for temperature, for an energy infrastructure type thing that might have infrastructure that is sensitive to rapid decreases. So quite a few motivations around having a very good physical representation, spanning uncertainty space, doing so at high spatial and temporal resolution, and trying to yield a lot or leverage a lot of observations, as you've probably gotten a sense of through this. Before I kind of progress onto some of the details of this, if you guys are familiar with CORDIF approach, that sort of regression, diffusion type of architecture, quite a few modifications herein, but that's sort of what's at the core. And this is running single ensemble members in about 6 seconds per hour of forecast time. So we're able to configure this in a way where we're spanning full CONUS at 15-minute cadence of initialization from observations, and really just trying to stack that out on a single H100 GPU. If you can go to the next slide, Arun. So as I noted, a lot of our motivation is to have a good emulator, but also to leverage a lot of information that we know has a lot of value already in the forecasting space, and to also be able to leverage observations a little bit more flexibly too. So as some of the previous presentations have noted, the initial times, the spin up of high resolution models are really a challenge. Typically don't train on them, and those for the same reasons that you have difficulties in those cold starts and initializations and even the data assimilation of radar. We also wanted to try and improve what can be represented from observations at really short latencies in a nowcasting framework all the way out to the short range. And so you kind of get a flavor of that through just looking at this slide demonstrating the different large-scale conditioning inputs that can be used, whether it's GEFS members, as you see in NVIDIA's releases, or IFS members that we want to retune to work with, or even some of the other models like ForecastNet, for example. When Randy gets to his part of the presentation, demonstrates the ability to use guided diffusion to assimilate our sounder observations into an actual forecast in a machine learning framework. We also want to then be able to take those models and have an approach already in place to get that to our customers in a high resolution framework. So this is also a large part of that bigger or broader framework for delivering information from the constellation to the customer. The last bit of this slide is, of course, that far left piece, the inputs. So you can see a handful of different things, whether it's individual stations, radar, or even RTMA, where we know that the current observed conditions can differ from the initialization, especially for some of these that have slower initialization cycles. And so we want to be able to deliver that information at kind of a more rapid update cadence on actually the cadence of the radar. So we take some approaches to be able to initialize directly from those observations with some mechanisms for swapping them in at inference time, after again training on the HER emulation type of approach. If you go to the next slide, Arun. So just giving an example of how this is looking in operations, and to kind of come back to some of those motivating factors. So on the top, we've got the deterministic HER running across. This is a good squall or a good system coming across central Texas and Oklahoma. And what we're really taking a look at here is sort of the evolution and representation of a cold pool event and a strong gust front coming across. So in that center panel is just an ensemble mean from a 50-member ensemble, a little bit more inflated ensemble size than we were running operationally. But you can see that it largely represents a lot of the same features. In this case, since it is just a statistical mean, it is smoothing a bit there, but we want to be able to come back and now look at this in the probabilistic framework, where we're evaluating the number of individual ensemble members exceeding certain thresholds. And so I've of course picked thresholds that make sense in this case to be able to demonstrate some impactful piece of information. If we look at the temperature in the bottom panel in the sort of second from left, I've thresholded that at 293 Kelvin, fairly arbitrary, but in this case, when we watch it loop through the event, we can see that that's sort of this area where the cold pool, it's much colder than the environment around it through those convective mechanisms. And we can see sort of the ensemble probability of that occurring, similar to the one next to that with the gust, exceeding 25 mile an hour sort of gust conditions. And that gives us some information that can kind of come back to our customers in that framework of a high resolution sort of uncertainty estimate In this case, one other thing that is a novel aspect is being able to take the initialization directly from that unified precipitation product, which over the US, where you've got good radar coverage, is very similar to just the MRMS product. While we're representing the HER physics, when we inject at inference time, the radar estimates of where precipitation actively is, through that approach, we can still get a good representation where the model will respond. It'll update that initial location, and other variables like temperature and wind gusts will respond to that having been corrected. I think that's still a large area of research for us, that as we explore also guided diffusion, for example, in initialization and data assimilation approaches, for our sounders, those are also highly relevant in this capacity. That score-based data assimilation to be able to leverage the OBS directly is, I think, a big area for us overall, one that resonates with our customer needs really strongly. If you go to the next slide, Arun, and can I just get a time check from you? If that's okay.
Yeah, I think you're doing pretty good.
Okay, so just some quick skill scores, and these particular metrics are really meant to, again, frame that same idea that I've been discussing about being able to, one, generate ensembles very quickly, because we know that in these cases where you've got extreme events, the double penalty that was discussed earlier, where HER, for example, being deterministic, you get a nice physical representation, but it will be penalized fairly severely when that is, slightly misplaced. And so we do see just the kind of thing that you would expect from going to an ensemble mean, where some of the air comes down. You aren't necessarily correcting biases in this framework because you are emulating HER, but we also see that when we start to inject those observations at real time, we see errors in precipitation rate come down, especially to some of the random air, as well as the related variables, things like gust. Another one that is a big one for us that you don't typically see or think of in these 15-minute things is things like visibility. So a case like that, sure, precipitation and visibility aren't necessarily concerned about, but the same model that we're demonstrating here is doing, for example, fog forecasting in San Francisco for aviation type of purposes, or many other customer sort of centric things. So a large number of considerations around the different skill scores that we work with. Another one of your cohort, Mariah Pope, who's at Tomorrow and works heavily in the EPIC program, for example, has been leveraging similar methodologies with a little bit different training loss functions for exploring hail and lightning with an approach like this. So being able to expand out the variable list from things that are typically thought of in this. So it's become a fairly flexible method for us to really explore a lot of our customer needs. And we do, again, just kind of think of that in terms of how does it connect back to the constellation. We want to be able to, as the field increasingly develops these very skillful models, these very great ML approaches, and they're increasingly open source and foundational as well, we're always kind of thinking of it from the perspective of how do we then leverage that to, one, make use of our sounders, the constellation that we've invested a lot in, and for the specific reason of how do those drive improved forecast for our customers and for the community. On to the next slide, Arun. So the other thing that's kind of cool about this too is when we take this approach of being able to leverage different pieces of information as available, hopefully you've gotten that flavor from us, whether it's the satellite precipitation retrievals that were discussed earlier, or the different inputs and targets that we have for the diffusion-based approaches. One of those is, of course, being able to expand out beyond just the US. And so exploring when we train the model on HER type of physics over the US, is it the kind of thing where there is any value expanding it outside? And this is an interesting case because we have run a very long archive and have a long running operational product and reanalysis of WRF over Central and East Africa, for example. So we can come back and evaluate what expanding out beyond just CONUS with this type of approach might look like. Also, where we don't have radar, how does it look when we try to use an emulated, a radar emulator from those different satellite channels, especially with the new media set coming online, MTG, this year. So I think there's a lot of opportunities to continue exploring. We see very good skill. We see some novel abilities here to just kind of, even if simply downscaling to resolutions that make sense and help for predictions in areas like this, very complex topography of East Africa, for example, but inheriting also just the ensemble spread from large scale models in a framework like this. There are a lot of opportunities to provide better forecast information than currently exists while we continue to explore this. I think on to the next slide, and that might actually kind of sum everything up for me. So I think Randy will take us through on how this kind of connects back to the constellation pieces. Thanks for the time.
Thanks, Forrest. Yeah, so we'll be zooming out here a little bit from the focus domain of trying to do these kilometer scale predictions to more of a broad scale, global perspective, especially because our sounders are collecting data everywhere. And that's kind of the view we're going towards as well, to leverage that on more of a global stage. So go to the next slide, Arun. So I think something we haven't even been able to contemplate is this new paradigm that tomorrow we're pushing, as well as other companies out there that are all doing low Earth orbit observations. We're starting to collect more and more Earth observation data that we've never had in the past. And the idea that maybe we could even postulate now is that, what if we had TMS plus an AI weather framework? Could we then initialize a forecast at a much faster cadence than we could previously because of compute restrictions? So the idea here, the x-axis is the forecast lead time, the y-axis is the forecast accuracy, and this is a gross underestimation of actually what weather forecasting does with time. But hopefully this illustrates kind of the idea, is that, go ahead, click Arun. If you were to reinitialize the forecast every hour or every time you get a new granule, you might be moving that forecast horizon inwards so that the forecast is easier as well as more accurate with time. And this is the general premise behind her, as well as I think the Warnock forecast. The idea is, if you kind of constantly assimilate new observations, you're moving that forecast window closer, and hopefully then your forecast is more accurate at longer lead times. So go ahead and click. A lot of the revolution that's come from weather forecasting in the AI space has been, the big perk is AI weather models run fast. And this is an example of me running Aurora on a single GPU. This one was just, I think, a few days, but yesterday I ran it for fun out for 21 days, and it runs in 10 minutes. And that's, I think a lot of people here are familiar with that new capability that we could never do before. And it's an exciting time to potentially launch full-fledged weather models at a much faster cadence than we could ever before. And I think that traditional data assimilation and NWP just can't handle the volume of data that we're starting to collect globally with all the government agencies, private sector, all that fun stuff. It just can't handle this rapidly updating global observations. So the NWP side, I think the solution, the AI weather models are there, but the DA focus has been, I think over the past 6 months to a year, a lot of the teams around the globe have started to focus in on how do we do DA now that we can have an end-to-end forecasting AI system. So just some examples would be like the direct observation forecasting system stuff that ECMWF has been working on, Alexi and others. I think there's a Christian Lessig paper out there looking at these direct observation prediction results, as well as the Aardvark paper is a good example, albeit at a lower resolution than we might want, of doing an end-to-end AI weather forecasting approach. But one technique that I personally find very exciting and applicable to a lot of DA tasks is the score-based data assimilation paper that came out of the University of Liège in Belgium. And if you want to click to the next slide, if you're not familiar with this technique, it's this idea of guided diffusion, where you have a diffusion model that generates an initial weather state that knows the relationship between the pressure gradient force and the wind speeds, and it knows the Coriolis force, and it learns these physical processes through seeing millions and millions of images and constantly having to reconstruct noised or destroyed images. So it learns the relationships between all the various parameters. And the big perk is that of course, it does take a lot of compute to potentially train this model, but then after training, you can then guide the diffusion without having to train with any specific observational set. So this is particularly interesting for us at Tomorrow because we've only had about a year of our own TMS sensors on orbit, so it's clearly not enough data to train a robust, large-scale global model out of at this point. So the cool thing about using score-based data assimilation is that we don't have to necessarily train on TMS data preemptively. We can then just incorporate it at inference time. Say we have some granular data, and we can then slide in what that new updated temperature profile is or the humidity profile to guide that initial state into a better representation of the actual truth, as opposed to a previous forecast time or et cetera. There have been a lot of examples, and I encourage people to read these papers. A lot of them are preprints. I apologize that the field has a bit of a drowning problem with preprints, and there's a lot out there. But if you're interested in score-based data assimilation, this Munchak paper is pretty good. Recently, there's the Martin et al. Paper looking at oceanography data assimilation. And then the original Rosette and Lupe authors are also on this Andrew paper where they have extended it to a global model instead of just showing toy examples. So please check those out. But on the next slide, we have started to test this out and figure out how we incorporate our constellation data. And Arun showed earlier how we're retrieving profiles of temperature and humidity with our sounders. So this is the idea that we're kind of coming up with of using our retrieved satellite products to then guide the diffusion to update those fields. So here's an example, a toy example of 850 hectopascal specific humidity. The right top plot shows what the TMS data observed on this day, where the warmer colors are higher humidity values, cooler colors are lower. And then when we use the guided diffusion approach versus like if we take a random weather scene versus one that was guided with the TMS data, you can see how the guided diffusion is not only just cutting and pasting the data into the framework. It says, well, in order for me to have this ribbon of high humidity in the Pacific here, I need to then adjust the humidity elsewhere to make sure that it's still physically consistent. So it's encouraging to see that the model is adjusting data well with outside the swath to adjust that data within the swath and match much more faithfully. And it's exciting to see that we could get it to run with our actual TMS data. So this is an initial proof of concept here. We're working on extending this out, and hopefully we'll present some more results at future conferences.
Okay, so thanks, guys. I'm just going to bring it back. The question is, where do we see AI ML, at least in our vision? We see it everywhere, and we're kind of introducing that in all of these places. And I'm kind of reminded about 4 years ago, my wife asked me innocently, how does she see ML techniques in weather modeling? And I told her it'll never work. Since then, I've probably gained 20 pounds eating crow. She still reminds me of that. And I will tell you, when I saw the first Pango paper, I jumped out of my chair. I'm sure many of you all did. And since then, the journey has been incredible. I think just to conclude, we see that the ML revolution in weather modeling is similar, maybe even not bigger than the ML revolution that came when we actually put numerical weather prediction models. And we are working very closely with NOAA, academia, and private sector partners. We're focused on developing satellite products, building ML-based data assimilation, and enhancing weather forecasts for nowcasting, regional, up to global medium term. So with that, I'll open it up for questions.
Hey, Arun, I just want to add a comment to that I think you forgot the fundamental presumption that wherever there is a data, there is an AI, so you can't beat that, right?
That's true. So with that, if there are any questions, and there will be talks. Randy's going to be there at the ECMWF. We're going to come at UIFCW. We're excited to present our results, and we're going to be having a few publications coming online. So we're available any of the time. And of course, we're still involved with Epic a lot. So these are very exciting times for all of us.
Okay, just want to say thanks to Arun, Forrest, Randy, the Tomorrow IO team. Any questions for him? I didn't see any in chat. I was kind of monitoring it, but we do have time for a question or two if anybody has one. Okay, hearing nothing. Thank you very much. That was a great talk. I really appreciate the team's forward look there. And with that, we'll move on to the next presenter. Thank you.